Hello dear learners, welcome to yet another lecture on dynamic programming. In this lecture, we will study about matrix chain multiplication. So first let us revise what is matrix multiplication. So we have two matrices A and B. If we want to multiply any two matrices A and B, then we need compatible dimensions. So what are compatible dimensions? It means that if the dimensions of A are m cross n, means there are m rows and n columns, and the dimensions of B are n cross p, means n rows and p columns, then we say that their dimensions are compatible. Why? Because the number of columns in the first matrix should be equal to the number of rows in the second matrix, right? And the product which we obtain has dimensions m cross p. Okay, so let us take an example. Suppose A is 2 cross 3 and B is 3 cross 2. So here the number of columns in A is equal to the number of rows in B. So we say that A and B are compatible for matrix multiplication. Okay. So suppose A looks like this. There are 2 rows and 3 columns. So 2 rows and 3 columns. So this is the structure of A. And what is B? B has 3 rows of 2 columns. Okay. And when we multiply them together, then here the first cell, the value of the first cell is obtained by multiplying element wise this row of A with this column of B. So element wise multiplication means this element is multiplied by this element is multiplied by this element is multiplied by this element, and we add the products. Okay, so this is how we obtain this cell, and for the next cell we do the same. This row is multiplied by this cell. Okay, so here we get it. Okay, similarly when we move down here, this cell is obtained by multiplying element wise the second row with the first column of B, and this cell is obtained by multiplying the second row with the second cell of B. Okay, so the overall, this is AB, and the overall number of rows and columns in this matrix, the resultant matrix is 2 cross 2. Okay, so M N N P. Okay, the resultant matrix has dimensions M cross P, that is 2 cross 2, right? So particularly if we have any cell whose indices are I comma j. Okay, so let us talk about this index. Okay, so this is index 1 comma 1, this is 1 comma 2, this is 1 comma 3, and this is 1 comma 4. So here I is 1 and j is 2, and it is equal to a I comma 1 into b 1 comma j plus a I comma 2 into b 2 comma j. Okay, so till n, what is n here? N is 3, right? So n is 3 here. Okay, so plus a I comma n, that is 3 into b 3 comma 3 comma j. Okay, so this is the exact expression. So what is this expression doing? So we were talking about this cell, right? So in the previous explanation I told that this can be obtained by multiplying this entire row element wise with this entire column. Okay, so what is this? This is 1 comma 1, and here we are multiplying it with this is okay. Let me write first 1 comma 1, 1 comma 2, 1 comma 3. Similarly, this is 1 comma 2, this is 2 comma 2, and this is 2 comma 3. Okay, so we are multiplying 1 comma 1 with 1 comma 2, so this is what is written here. The next we are multiplying 1 comma 2 with 2 comma 2, so this is the expression. Then 1 comma 3 with 2 comma 1 comma 3 with this is, yeah, there is a mistake here. This is row 3 and column 2. Okay, so 1 comma 3 with 3 comma 2. Okay, so now each entry in AB, it means takes order of n steps to compute, right? So this one entry, this single entry, how many steps it required? It required 3 steps, right? 1 comma 1 with 1 comma 2, this was the first step, and the second step was 1 comma 2 with 2 comma 2, and the third step was 1 comma 3 with 3 comma 2. Okay, so total there were 3 steps. And where did it came from? The 3 came from the value of n. Okay, so we can say that each entry takes order of n steps to compute, right? And this is about one entry. How many total entries are there in your matrix? In the resultant matrix, there are m rows and p columns. Okay, so overall the total number of steps will be m cross p cross n, right? M is the number of rows in the resultant matrix, p is the number of columns in the resultant matrix, and n is the number of steps which are required to compute one entry, one cell, right? Okay, so the matrix multiplication which we described is associative. What is associativeness? Associativeness means if you have to compute A into B into C, then the placement of parentheses does not matter. Okay, you can first compute A into B, right? And then multiply the resultant matrix with C. Or you can do the other way around. You can first compute the product of B and C, and then you can multiply the resultant matrix with A, right? And another thing to note here is that A into B is not equal to B into A. Okay, so these two things are not same. So you cannot write that first I compute B into C and then I am multiplying with A. Okay, so A should be on this side, only then this is valid. Okay, so okay, this is fine. Now bracketing, here we were bracketing, we are putting the parenthesis. It does not change the answer, right? But it can affect the complexity of computing the product. Okay, so how does it affect the complexity? Complexity means the total runtime, the total number of steps. So let us take an example to understand this. Suppose you have matrix A 1 cross 100, B 100 cross 1, so you can see both are compatible. Then you also have C, which is 1 cross 100, right? And you want to compute the product A, B, C, right? So you have these two options. Okay, so if you pick the first, pick this option, A multiplied by the product of B and C, then what will happen? First you will compute B into C. So B into C, they are compatible with each other, and when you will multiply them, then the resultant matrix, its size will be 100 cross 100, right? BC is 100 cross 100, and the number of steps, how many number of steps will be taken to compute this? As we saw in the previous slide, the number of steps are equal to m into n into p, right? So m, n and p, these are the values here. M is 100, n is 1 and p is 100. Okay, so the total number of steps required to compute b into c is 10,000 number of steps. Okay, so now we have computed this. Next we will multiply a with this thing. Okay, so then a is 1 cross 100 and b is 100 cross 100, right? So both are compatible, right? Then how many, what will be the, first let us talk about the dimension of this complete product. It will be 1 cross 100, right? 1 cross 100. And number of steps required by it will be equal to m n p. So 1 into 100 into 100. So 10,000 steps, right? Okay, so now let us move to the next option. The next option was first compute a into b and then multiply it with c. Okay, so a into b. A is 1 cross 100 and b is 100 cross 1. So AB will be 1 cross 1 and the number of steps will be m into n into p. 1 into 100 into 1, 100 steps. Okay, and then we multiply it with c. Okay, so AB is 1 cross 1 and C is 1 cross 100. Okay, so when you multiply them, the resultant matrix will be 1 cross 100 and the number of steps required by it will be 1 m cross n, that is okay, so I think I'm making a mistake here. So AB is 1 cross 1 and C is 1 cross 100, right? And the resultant matrix will be 1 cross 100, right? And the number of steps will be m into n into p. So 1 into 1 into 100. So total 100 steps. Now can you see the difference? Here we are using double number of steps. Here we are using only 100 steps. Here we are using 10,000 steps. So it makes a huge difference. It depends on the way how you are putting the parentheses, how you are chaining the matrices. So it is very crucial if you want to decrease your total number of steps, if you want to minimize the cost of multiplying the matrices, then you have to put the brackets, you have to put the parentheses in the optimal way. Okay, so this is the problem of matrix chain multiplication. So let us move to the problem statement. You are given a number of matrices m1, m2, mn, and each matrix has dimensions. So m1 has dimensions r1 into c1, where r1 is the number of rows in m1 and c1 is the number of columns in m1. Similarly, m2 has certain dimensions, mn has certain dimensions, and dimensions are such that you can compute m1 into m2 into mn. Okay, suppose you have three matrices m1, m2 and m3, and m1's dimension are 1 cross 2, its dimension are 2 cross 3 and its dimension are 3 cross 4. Okay, so now we see that here the dimensions are matching, right? You can compute m1 cross m2 cross m3. Okay, because here this is r1 c1 and this is r2 c2, this is r3 c3. Okay, so c1 is equal to r2 and c2 is equal to r3. Okay, so if this is the case, then you can say that the dimensions are matching. Okay, so this is what I'm saying. C1 Ci is equal to Ri plus 1. Okay, C1 is equal to R2, C2 equal to R3, C3 is R4, and so on for all I ranging from 1 to less than n, right? Okay, and our problem is to find an optimal order to compute the product. Bracket the expression optimally so that the cost of forming the matrix chain multiplication is minimum. We are minimizing the cost here. Okay. So in this problem, we have a number of subproblems. So let us look at these subproblems. So we see that the product can be computed by multiplying m1 into m2 into m3 and so on till mn. Okay. So your final step will comprise of two subproducts. What are those? The first will be the first set of matrices. Suppose it is m1 into m2 into m3 and so on into some mk. Okay, so if you have suppose m1 to m7, these are the number of matrices, then your final not m7, let us take a smaller number, m4. Okay, so your final step, what it will comprise, it will comprise two subproducts. Okay, so the first one can be m1, the second can be m2 into m3 into m4, right? Or it can contain m1 into m2, then m3 into m4, or it can have m1 into m2 into m3 multiplied by m4. Okay, so these are the possibilities. So this is what this statement is saying, that the final step is containing of two subproducts, m1 to mk and then mk plus 1 to mn. Okay, so here m1 and mn, in this particular example n is 4. Okay, so if you look at this particular order, this particular bracketing of matrices, then you see that it is m1 only. So here k is 1, and then here we are starting from k plus 1 to mn, where n is equal to 4. Okay, and in this second bracketing, k is 2, and here you are starting from k plus 1. Here k is 3, right? Like this. For some k less than equal to greater than equal to 1, less than n, right? So the first subproduct, these are two subproblems, right? Two subproducts. The first subproduct has dimensions r1 into ck, right? So number of rows in the first matrix and the number of columns in the second matrix. Okay, so if you look here, then this m1 is the first subproduct and the second subproduct contains m2 into m3 into m4, right? Okay, so I think it will be difficult. Let me take a simpler example. Let us look at the second bracketing option, m1 into m2 and then m3 into m4. Okay, so suppose you are having these two subproducts. Okay, so what will be the dimension of the first subproduct? m1 has dimensions r1 into c1 and m2 has dimensions r2 into c2, right? So what will be the dimensions of this subproduct? It will be m, and the number of rows will be equal to m1's rows, r1, and the number of columns will be c2. Okay, so this is what this statement is saying. And similarly this, here in this particular example, k is 2, right? So the dimension of the second subproduct, it will be r3 into c3 multiplied by r4 into c4. Okay, so from this we will get r3 into c4, right? So this is what this thing is saying. So it is saying it is r k plus 1, yeah, because k is 2 here, into Cn. N is 4 here. Okay. And when you multiply these two subproducts together, then what will be the cost? This is the final step. Okay, so we are talking about the final step, and the final step's cost will be m into n into p. Okay, so these are the dimensions of the first subproduct, and these are the dimensions of the second subproduct. So this is our m, this is n, and this is n, this is p, right? So C2 and R3 will be equal to each other, right? So it will be R1 into C2 into C4, okay? So just think, R1, C2 means CK. In general, it is CK, right? Because K is 2 in this particular example. And then Cn, right? It means the dimension, the number of columns in the last matrix. So this will be the cost of your final multiplication step. So what will be the total cost? Total cost will be the cost of computing the first subproduct plus the cost of computing the second subproduct plus doing the multiplication of these two subproducts. Okay, so you can see here this is a recursive computation, right? So recursive computation has overlapping subproblems. So there are subproblems which if we just implement simple recursive algorithm, we will encounter subproblems again and again. Okay, so in order to avoid this wasteful recomputation, we will switch to dynamic programming. Okay, so the question here is, which k should we choose such that we have the minimum cost, right? So as I already told you, there is inductive formulation. Recursion is there in this particular problem. Okay, so if you talk about cost of the entire matrix chain multiplication starting from m1 till mn, then it will be the minimum. Okay, again let us take this example to understand. M1, M2, M3 and M4 are your 4 matrices. So n is 4. Okay, so we want to minimize the cost. Okay, so it will be, the minimum cost can be chosen by varying the value of k. So when k is 1, k is starting from 1. Okay, when k is 1, then it means the first subproduct is m1 and the second product is starting from k plus 1, that is m2 to m3 to m4. Okay, and yeah, so it will have some cost, plus it will have some cost, plus when you multiply them together there will be some cost, which will be R1 into C1 into C4. Okay, because k is 1 here, that is why I have written C1. When you choose k equal to 2, then again you will have some cost of multiplying m1 into m2 plus cost of multiplying m3 into m4 plus cost of multiplying these two subproducts, which will be R1, C2, C4. Similarly, when k is 3, then it will be cost of multiplying m1 into m2 into m3 plus cost of multiplying m4 plus the cost of multiplying these two subproducts, which is R1, C3, C4. Okay, and now this is the last option which we are having, because k is less than n. Okay, so these are three options and we have to choose the minimum of this, right? So that will be our solution. That is the inductive formulation. In general, it is not necessary that the matrices will always start from 1. You will always have to compute starting from 1. It can start from any I. Okay. So cost of multiplying the matrix mi into mi plus 1 and so on till mj will be the minimum of the cost of multiplying the subproduct starting from mi plus 1 and so on till mk plus the cost of subproduct mk plus 1 till mj plus the cost of multiplying these two subproducts together, which will be, because this is starting from I, Ri into Ck into Cj. Okay, so the value of k varies from I. It means the k is starting, if k is greater than or equal to 1 and less than greater than equal to I and less than j. Okay, so out of all these options which you have for k, you will pick the minimum. Okay, so this is the recursive or inductive formulation for this. Okay, so what is our final equation? So let us first rewrite this thing, cost mi till mj, by this shorthand notation, cost ij. Cost ij simply means the cost of multiplying the matrices starting from mi till mj. Okay, so if cost of ij is 0, it means you are not doing any matrix multiplication. Okay, otherwise the cost of ij will be the minimum over k, where k varies from I till j minus 1. Okay, so you have this thing, cost of the subproduct starting from I to k, the cost of the subproduct, here there is a mistake, it will be k plus 1 till j. Okay, this is not like this, because the second subproblem will start from the matrix mk plus 1 till j, because the last matrix here is j, and plus the cost of multiplying these two subproblems together, which is ri into ck into cj. Okay, and we compute this cost ij only when I is less than or equal to j. Means we are not multiplying m2 with m1. Right? We are multiplying m1 with m2. Okay, so the order must be maintained, because m1 into m2 into m4, the matrices are like this. Okay, so you cannot change this order, because as I already told you, m1 into m2 is not equal to m2 into m1. Okay, so you will multiply only when I is less than or equal to j, right? Okay, so now we are ready to understand this with the help of example. So here is this example. Here you have an array dimensions. Okay, this is given as input and it is storing the dimensions of the matrices 4, 10, 3, 12, 27. Okay, so what does this mean? This means that there is an array M1 whose dimensions are 4 into 10, right? The next array is M2 whose dimensions are 10 into 3, okay? And then we have M3 whose dimensions are 3 into 12, M4 its dimensions are 12 into 20, M5 the dimensions are 20 into 7. So there are total 5 matrices. Okay, so because the dimensions are compatible to each other, so we are not redundantly storing the same thing again and again, because we know that we can perform the matrix chain multiplication only when the dimensions are compatible with each other. When the dimensions are compatible with each other, when the number of columns of the previous matrix are equal to the number of rows of the next matrix. Okay, so this is a simpler way of storing the dimensions of the matrices in the matrix chain multiplication. Okay, so this is the thing which I wrote here. So now, similar to the other DP problems, here also we will create a matrix. Okay, and now this will be a n cross n matrix, where n is the number of matrices you have. Okay, so here we have 5 matrices. We are creating a 5 cross 5 matrix. Okay, okay, so let's move back here. Yeah, so how to solve this? So the first or the base case is when there is a diagonal, that is when you have I comma I in this matrix. Suppose this matrix is DP. So you will simply make it equal to 0, because we are not multiplying M1 with M2. M1. We are not multiplying M2 with M2. Okay. So simply we are not performing any multiplication, and as I wrote in the previous slide, the value of dp I comma j is 0 when you are not performing any multiplication. Okay, so we are not performing any multiplication when I is equal to j. Okay, it means when it is I comma I. Okay, so we can simply make 1 comma 1 0, 2 comma 2 is 0, 3 comma 3 is 0, 4 comma 4 is 0, and 5 comma 5 is also 0. Okay, and one more thing which I talked about in the previous slide is that we perform multiplication only when I is less than j. Okay, so we do not perform any multiplication when I is greater than j. So here it is I and here it is j. Okay, and if you look at this cell, here I is 2 and j is 1. So will we perform any multiplication? No. So we are not performing any multiplication here. Similarly here also, because this I is 3 and j is 1. Here also, we are not performing any multiplications. Okay. Similarly, if you go here, I is 3 and j is 2. So you are not doing any multiplication. 4, 2, 5, 2, 4, 3, 5, 3, 5, 4. Okay. So this is, we do not need to bother about the cells which are below the diagonal. Okay. So these are already eliminated from our consideration. Okay. So now how will we move on from here? Here we will pick this cell first. Okay, so in this cell I is 1 and j is 2. Okay, so I is less than j. We are doing a multiplication, and it means that I is 1 and j is 2. So we are multiplying starting from M1 till M2. Okay, so as we saw in the previous slide, that it is M I till Mj. Okay, so I is the starting matrix and J is the ending matrix. Okay, so now we have two matrices, M1 and M2. Okay, so here K, what can be the value of K? Okay, so K can be, let's look at the equation which we used in the previous slide. K varies between I and J. Okay, so here I is 1 and J is 2. Okay, so K should be less than 2, K can be equal to 1. So only option which we have is K can be 1. Okay, so it means the first subproduct contains the matrix M1 and the second product contains the matrix M2. Okay, so it means that we will add together the cost of multiplying M1 plus the cost of multiplying matrix M2 plus the cost of multiplying the matrices M1 and M2. Okay, so what is the cost of matrix M1? It means we are not multiplying, it is only M1. Okay, so there is a single matrix, it means we are not doing any multiplication, so its cost is 0. Similarly, cost of M2 is also 0. For this we will look at M1 comma 1, right? M1 comma 1 is 0. For this we will look at M2 comma 2. 2 comma 2 is also 0. Plus, what will be the cost of M1 into M2? It is R1, then C1 and then Cn. Okay, R1, C1 because K is 1 here and Cn. N is 2 here. Okay, the last matrix is M2. Okay, so the number of rows here are 4. R1 is 4 multiplied by C2, it is 10, C1 sorry, and C2 is 3. Okay, so total it is 120. The 120 is the cost. Okay, okay, so we have done this. Now we will move to this cell. Okay, what is this cell? This cell is 2 comma 3. 2 3. So it means M2 and M3. So I is 2 here and J is 3 here. Okay, and the K can be greater than or equal to 2, K should be less than 3. Okay, so the only option here we have K is 2. Okay, so it means we have two subproblems. The first is M2, the second is M3. Okay, so cost of M2 means M2 comma 2 which is 0. Cost of M3 means M3 comma 3 which is 0, and then the cost of multiplying M2 and M3 together which is R2, then C2 and C3. Okay, so it will be R2 is 10, C2 is 3 and C3 is 12. It is equal to 360, right? Yeah, it is 360. Okay, so similarly we move here, it is 3 comma 4. Okay, so 3 let me simply do it. So 3 comma 4 means the K can be 4, right? Because K should be less than K can be 3 because, okay, let me write it here. So it is 3 comma 4. I is 3, J is 4. So it is M3 into M4. So it means it should be 3 here, it should be 4 here. So K can be 3. And the two subproblems which we are having here is M3, M4 and then M3 comma 4. So cost of M3 is 0, cost of M4 is 0, and the cost of M3 comma M4 is 3 into 12 into 20. What is it? It is 720. Okay, so we fill it here. Similarly, we move here and here in the similar fashion we will obtain its value, because here also the only two matrices are involved, 4 and 5. So M4 into M5, the cost is 1680. Okay. Okay, so now we are ready to move here. Here I is 1 and J is 3. Now we are considering three matrices. What are those matrices? M1, M2 and M3. right? And now you will see the difference in this example. Here k is less than equal to 1 and k is greater than equal to 1 and k is less than 3. Now we have two options for k. K can be 1, k can be 2, right? So when, let me first erase this. When k is 1, it means on one side you have m1, so you will take cost of m1, and on the other side you will have m2 and m3, right? And then you will take the cost of multiplying these two subproblems together, and it will be r1, c1 and c3, right? Okay, so what is the cost of m1? It is 0. Cost of m2 and m3, it is 360, because we have already solved this problem. It is 360 plus r1, c1, c3. So r1 is 4, c1 is 10 and c3 it is 12. Okay, so the overall cost will be 0 plus 360 plus this is 480, I think. So the overall cost, it will be 840, okay, when k is 1. So the first option you have is 840, and now next option is when k is 2. So when k is 2, it means in the first subproblem you have matrices up to 2, and the remaining matrices will go to the second subproblem, and the overall cost will be r1 into c2, because it is m2 here, into c3, okay, and the cost of m1 m2 is 1 into 2, this is 120 as written here. Cost of m3 is 0, and this cost, it is r1 4 into c2, this is 3 into c3 12, okay, so it is 120 plus 144, and overall it is 364. Okay. So these are the two options, right? And you will pick the minimum of this. The minimum is 364. Okay. So you will choose this. Am I doing it right? It is not 364, it is 264. Okay. Okay. So similarly, you will now move to this cell, which is 2 comma 4. So your matrices are starting from matrix 2 till matrix 3. Okay, sorry, 4. So 2, 3, 4. So k here is starting from 2 and k is less than equal to 4. So you have two options for k. K can be 2, k can be 3. Okay. So when you have k equal to 2, it means on one side you have matrices till 2. Okay. So it means m2 is there. Then you have cost of remaining matrices k plus 1, that is m3 till kn, m4, plus the cost of multiplying these two subproblems together, which will be r2, c2 and then cn, that is c4. Okay, and when k is 3, then you have on the first subproblem you have matrices till 3. So m2, m3 are there. Then in the second subproblem you have whatever is left, only m4 is left, plus the cost of multiplying these two subproblems together, which is R2, C, here it will be C2, okay, because only one matrix is there. Here it will be C3 and C4, okay. So whatever is the cost, you will pick the minimum of these two costs, and it will be 320, okay. So I'm just writing it here, you can verify it yourself, okay. It is 320. Similarly, for here also, now you will have 3 to 5 matrices 3 to 5 will be considered. So K has two options, 3 or 4. Okay, in the similar order you will compute for the two options when K is 3 and when K is 4, and you will pick the minimum and you will get the answer. It will be 1140. Okay. Okay, so now let us move to this cell. It is 1 comma 4. Now the matrices are varying from 1 till 4. Okay, so you have 4 matrices. It means the choices of K are varying from 1 to 4. K can be 1, K can be 2, K can be 3. Now you have 3 choices. Okay, so let me erase these things here. When K is 1, it means you have only matrix 1 here on the first side, first subproblem. The second subproblem contains K plus 1 to Kn, that is M2, M3 and M4. And then you will find the cost of computing the product of these two subproblems, which will be R1, C1, C4 when K is 1. Okay. Similarly, when K is 2, then you will have cost of M1, M2 plus cost of M3, M4 plus the cost of multiplying these two subproducts, that will be R1, C2, C4, right? And similarly, when K is 3, it will be cost of M1, M2, M3 plus cost of M4 plus R1, C3, C4. Okay, so whatever is the minimum of these three, you will write here, and it turns out that it is 1080. Okay, similarly you will move to 2 comma 5, and here the matrices will vary from 2 to 5. Okay, so again you have three options for K, you have three options for bracketing. Okay, so M2, then M3, M4, M5, or M2, M3, M4, M5, or M2, M3, M4 and M5. You will you compute the cost of all three options, and you will pick the least, which is 1350. Okay, and finally you move here. Here your I is 1 and J is 5. So you have all the 5 matrices. We are considering all the 5 matrices here. And so K can vary from 1 to 4. So you have 4 options for parenthesizing. Okay. And same in the similar order as we did in the previous examples, you will compute the cost when K is 1, when K is 2, when K is 3, and when K is 4. And out of these you will pick the minimum. And the final answer is 1344. It means the best choice for parenthesizing these 4 matrices is the one when you have to perform 1344 number of steps. Okay, so this is the solution to this problem. And now let us look at this matrix chain multiplication algorithm. So here you are given the dimension matrix and the total number of matrices. Okay, and then you create this C matrix which we created in the previous example, which was 5 cross 5. And here we are not doing n cross n, we are doing it n plus 1 cross n plus 1, because array matrices, they start from 0. Okay, but in this example we are not using the 0 index. Okay, that is why we are doing it n plus 1 cross n plus 1. Okay, so as I told you, we are not utilizing the 0th index, we are starting from the first index. Okay, so the first is to make the diagonal elements 0. So for I equal to 1 to n, Cii is 0. Okay, and then this length variable, it is starting from 2 to n. Okay, so 2, 3, 4, when you have 4 matrices, when n is 4. Okay, and in the previous example we had 5 matrices, so it will run till 5. Okay, and this I loop will run from 1. So it will first compute this matrix. This is 1 comma 2. Okay, as we computed in the previous example, the first matrix which we computed, the first cell which we computed was 1 comma 2. Okay, so I is starting from 1. When I is 1, then j is I plus length minus 1. So when I is 1, j will be 1 plus length is starting from 2 minus 1. So 2. It means first we are computing 1 comma 2 and we are setting its cost equal to infinity. Okay, and then we are computing the cost for different choices of k. Okay, so k is starting from I and k is less than equal to j minus 1. Okay, and j should be less than n. So we are computing the cost as we did in the previous example. So the cost is Cik plus Ckij. So this is same. We are going from I to k, right? So if I talk about 1 comma 2, okay, then the one subproblem has matrix m1, the second problem has matrix m2, because we have only one choice for k, that is 1. Okay, so cost of ik, that is 1 comma 1, plus cost of k plus 1 comma j, that is 2 comma 2. So in this case both the costs will be 0. Plus then we will multiply the dimensions of these two matrices. So the rows of this matrix, which is stored in the array dimensions at location I minus 1. Okay, so this is the dimension matrix. So suppose it was 4, 10, 12, 3, 5, like this. Suppose, so the number of rows of the first matrix will be stored at the index 0. Okay, so that is why it is dimensions I minus 1 into dimensions k. Okay, because we have to look at the kth index. Here k is 1, so we will pick this, into dimensions j. Okay, so the last matrix is j matrix, so we will look at the dimensions j. Okay, so if the cost you are computing is less than the previous cost, yeah, then you will update the cost, because you are minimizing, trying to minimize the cost here. Okay, so in the similar fashion, then this loop will proceed further. So I will become 2 in the next step. In the first step it was 1 comma 2. In the second step I will become 2, and in this case j will be 2 minus 2 2 plus 2 minus 1, that is 3. Okay, so 2 comma 3 as we computed in the previous example. After 2 comma 3, then I will become 3. When I is 3, then j will be 3 plus 2 minus 1, that is 4. So 3 comma 4, like this we are going diagonally. Okay, okay, so I will vary till n minus length plus 1. Okay, so what is n? N is 5 minus length. Length is here, this length variable is 2. Okay, and plus 1. Okay, so 5 minus 2, 3 plus 1, 4. So till 4 it will move till index 4. Okay, so as we did here, it was moving till, first it computed 1 comma 2, then 2 comma 3, then 3 comma 4, and then 4 comma 5, right? Okay, so after the first this iteration, after computing 1 comma 2, 2 comma 3, 3 comma 4, and 4 comma 5, then we will increase the length. Okay, now length will become 3. It means we are now including 3 matrices. Okay, so again I will start from 1, and now I will vary. I will start from 1 and I will vary till n minus length, which is 3 now plus 1. Okay, so 4 minus 3 plus 1, it is 2. Okay, so here we can see it should vary 3 times. It is 1 comma 3, then 2 comma 4, then 3 comma 5. Okay, so n is 5, sorry. Okay, so it will run 3 times, 1, 2 and 3. I will vary this much. These will be the values of I, and j's values, j will be I plus length minus 1. So it will be 3. When I is 1, j will be 3. Similarly here it will be 4, it will be 5 here. Okay, then after this iteration, length will become 4. So it means you are including the 4 matrices. When you are including the 4 matrices, then I will vary from 5 minus 4. Now I will run 2 times, 1 and 2. Okay, so when I is 1, j will be I plus length minus 1, 1 comma 4 and 2 comma 5, which you can see here, 1 comma 4 and 2 comma 5. Okay, and finally length will become 5, means you are including all the 5 matrices. In that case I will vary from 1 and I will stop at 1. Okay, how? Let us see. N is 5 and length is 5 plus 1, so it is 1. I will vary from 1 to 1. Okay, and when I is 1, j will be I plus length minus 1, so it will be 5. Okay, so as you can see in the last case it is 1 comma 5. Okay, so this is the algorithm, and for each value of I and j we are computing the cost by varying the value of k starting from I till j minus 1. Okay, and whenever we get a minimum cost, we are updating the cell I comma j. Okay, and if we want to analyze this, then here we can see that this loop is running n times. Okay, and then this is the length loop. Okay, so it is running from 2 to n, so it roughly it is running n times, and inside this there is a I loop. I loop is running from 1 to n minus length plus 1. Okay, so it will also roughly, it is iterating over the matrix, so diagonally it is going from 1 to 2 to 3 to 4 to 5. Okay, so it is also roughly running n times. Okay, and here we have another loop, the k loop. K loop is running from I to j minus 1. Okay, so again if we want to compute it, then in the worst case it will run n times. Okay, so the overall complexity is n cube. Okay.